got a rational function here on number 5, and we're given the first derivative, we're given the second derivative. So, following our checklist, okay, we're going to start with the first derivative chart. We're going to move on to a second derivative chart. We'll look at intercepts, we'll look at asymptotes, and ultimately come up with a sketch. So, first derivative chart. We take our first derivative as it's given. We explore where the first derivative equals 0. And we explore where the first derivative does not exist. So because the first derivative was a rational function, for the equals 0 side, we take the numerator, set it equal to 0. For the does not exist side, we take denominator, set that equal to 0. All right, so on the equals 0 side, got this negative quantity equal to 0, can divide the negative out. We're solving for x. Well, I'm going to add 1 over, divide by 3, and then take the square root of each side. And understand as I'm taking the square root because I'm solving, I've got the plus or minus aspect. You take the square root of 1/3, well, you're going to get the square root of 1, which is 1 over the square root of 3. But because eventually I'm going to graph this out, I'm going to go ahead and take the decimal approximation here. That decimal approximation, when you take 1 and divide by root 3, comes out to be 0.577 if you round to 3 decimal places. So it's going to be plus or minus 0.577 for x when the first derivative equals 0. On the does not exist side, all right, we've got x squared times a quantity that's squared. Now, for this x squared right here, one of our x's, as far as a solution to this equation is concerned, one of our x's is going to be 0. Now, you've got this quantity squared right here that's also equal to 0. If you take the square root of each side, that would get rid of the squared piece, right? You'd have x squared minus 1 equals 0, so x squared would equal 1. If you take the square root of both sides, you got the square root of 1. Take the square root means plus or minus, so plus or minus 1 is going to be another solution here. So this is going to be a pretty healthy chart we got to set up, right? Because we're exploring intervals starting at negative infinity, going to infinity, and we're hitting all these values in between that we found for x. So I'm going to make a little room here as I set this up. Let me get this part out. We're starting at negative infinity, working our way up to the smallest x value that we found out of all these solutions. So that smallest x value is going to be negative 1. At negative 1, we know the first derivative does not exist. We go from negative 1 then up to the next smallest x value that we found. And recall that the plus or minus 1 over root 3 here that we got, that was plus or minus 0.577. So negative 0.577 would be the next smallest x value. At negative 0.577, we know the first derivative equals 0. From there, let's see, next smallest x value we found was 0. Pause at 0, where the first derivative did not exist. We go from 0 now up to 0.577. 0.577, first derivative equals 0. Getting closer. 0.577 to the final x value we found here of 1. 1 derivative did not exist. And we get to our last interval, just enough room. So at this point, we've got our intervals set up, and we are taking values on each of these intervals. We are plugging in to the first derivative to see what kind of answers we get back. So I've got to take a number, for instance, on that first interval from negative infinity to negative 1, something less than negative 1. So I choose negative 2. I've got to take -2, go back here to the first derivative and plug in. All I care about is the sign result. If I plug -2 in, you know what you get? Should get something negative back. And if we get something negative back, what that tells us about the function then is the function is decreasing for that interval. All right, so we follow the same pattern throughout. I pick a number from -1 to -0.577, so -0.9, right? That'd be in between those numbers. If you take a -0.9, you go back to the first derivative, you plug in. Again, we should get something negative back. So function is decreasing again for that interval. At this point, right, hopefully we understand how we're plugging in. Okay? If we understand how we're plugging in, how this plays out, to kind of save ourselves some time here, it's positive on this interval, so function increases there. It's positive on this interval, so it increases here. It's negative on this interval, so it decreases. And then it is negative on that final interval, so it also decreases there. Now add the last column here for extrema as a review. Remember, we're going to have relative max or relative min points wherever we have a change in direction. So there is a change in direction from the interval -1 to -0.577 to the interval -0.577 to 0. Right? It goes down and then it goes up. So it's going to bottom out there. There's going to be a relative min. Now, since there's going to be a relative minimum at this x value, we need to know what the value of the function is there so we can use that point. If you take -0.577 and you plug back into your function, so now we're going back here, plug that in, we get 2.598. And we had another change in direction. We had a change in direction right here. Graph was going up, graph was going down. So it goes up, it goes down. You've got a relative max. Since we have a relative max there, it's worth finding that point at 0.577. So once again, we take that, we plug back into the function, we get -2.598. So in a minute here, when we get to the sketch, we've got some direction. We've also got a couple of points to play with because we got a min and a max. All right, so we move to the second derivative. For the second derivative, as it was given, we split it up to look where it equals 0 and where it does not exist. Got that numerator portion set equal to 0, got that denominator portion set equal to 0 for each of the respective pieces. If we solve this first equation, got this 2 hanging out in front, so we could divide that out. Then you've got 6x to the fourth minus 3x squared plus 1 equals 0. Kind of looks like a quadratic in disguise, kind of looks like something you might be able to factor out. It turns out this is not factorable. So the other strategy would be let y equal that 6x to the fourth minus 3x squared plus 1, right? Graph it out. See where it crosses the x-axis, right? That would be the solution then for x. So let's try that. All right, so we graphed it out. We're looking to see where it crosses the x-axis so we can find our solutions for x. How are we doing on those solutions? There are none, right? There's no solution for x here. It doesn't cross the x-axis. So this side doesn't work out. No solution on this side. on the does not exist side, looks like we got a similar scenario playing out to what we did with the first derivative, right? Got some similar pieces here, only now it's cubed instead of squared, right? But as you solve that out, you're going to get the same answers back as we did for the first derivative side, where it did not exist, and that should make sense. If it does not exist for one, well, chances are it's going to carry through and not exist for the other piece as well. So 0 plus or minus 1, we'll have those same key players as we did before. So setting up the intervals off of those three values now that we have, we're going from negative infinity up to negative 1. At negative 1, we acknowledge with the second derivative that it does not exist. We go from negative 1 to 0. At 0, we acknowledge second derivative does not exist. From 0 to 1, pause at 1, does not exist at 1, and then we go from 1 to infinity. In fact, when you look at that does not exist aspect for the second derivative and how it compares to the first, it should be consistent. And when you have existence issues for your derivatives, there's a chance, too, it could connect directly back to the function if you plug back in there. Right? There could be some domain issues here. So, we're back to analyzing intervals here, picking numbers on those intervals, plugging in now to the second derivative to see what kind of signs we're getting back. So if I take a number that's less than negative 1, say negative 3, plug back in here to the second derivative, see what kind of answers we get back. Looks like this go around, we should get something negative there. So what that means about the function, it means it's concave down for the curvature. From negative 1 to 0, if I select a number there, say negative 0.5, plug into your second derivative, should get something positive back there. So since we get something positive back there, that means the function is concave up on that interval. Once again, continue with the same pattern. If you analyze 0 to 1, on 0 to 1, we find we get something negative there. So that's concave down. From 1 to infinity, it's positive there. So that's concave up. Now, I've added the column here for inflection points. And inflection points occur when there's a change in concavity. So it might appear that there's an inflection point right here surrounding negative 1, right here surrounding 0, and right here surrounding 1. So the question is, are there actually inflection points there? Well, if there are inflection points, then we're supposed to be taking these values at 1, at 0, and at negative 1, and plugging back into the function. When you go back to the original function, you try to plug in negative 1, 0, and 1, you find that none of those values are in the domain. And since those values don't exist for the function, that means there are no inflection points over here. Now, had you plugged back in, you got a value back, then okay, you would have an inflection point for that respective value. But here, it doesn't work across the board. All right, so we got the first derivative chart, we got the second derivative chart. I'm going to review now some intercept ideas and some asymptote ideas. Whenever you find an x-intercept, you're curious to know where y equals 0. All right, so where y equals 0, we got to go back to the original function. F of x, y, same thing. So we're going to take the f of x idea out, put 0 in. 0 would equal, for the original function, 1 over x cubed minus x. The idea in finding these intercepts is maybe we can get some more specific points here to work with. So if we try to solve that, Well, basically you'd be multiplying both sides by that x cubed minus x, right? Be swinging this over to the other side, trying to clear that out. Of course, if I multiply both sides by this idea, obviously it cancels from the right, but if I multiply the left, I get 0. So 0 equals 1, meaning all my x's are gone and there's nothing to solve for. So, since there's nothing to solve for, there's no x-intercepts. But if you have resulting x's to solve for, you solve for those. That gives you specific points on the x-axis that you can plot. On the y-intercept side, we're looking to see where x equals 0. All right, so where x equals 0, we might have an idea where this is going already because of the results we got back on the chart. But f of x or y equals our original function, which was 1 over x cubed minus x. If I'm replacing those x's with 0, I've got 0 cubed minus 0 in my denominator, meaning I've got 1 over 0, right? Is that going to work? Yeah, y equals 1 over 0. That's not going to work so well. That does not exist. So we didn't get a solution back for y either. But had we gotten a solution back for y, that value we could plot on the y-axis, right? Just another point we could work with. But reviewing how to find intercepts, no real luck here. No x-intercept, no y-intercept. All right, reviewing how to find a vertical asymptote. Vertical asymptote is when the denominator is set equal to 0. All right, if we set that equal to 0 and solve for x, that gives us potentially our vertical asymptotes. So denominator in the original function was x cubed minus x. I'm setting that equal to 0. I'm solving for x. If I factor out an x to get started, well, basically you've got x out here as a factor, so x equals 0 would be a vertical asymptote. You've also got this x squared minus 1 idea. That would equal 0. Where if you add the 1 over and take the square root of each side, there's that plus or minus 1 again. So x equals 0, x equals negative 1, x equals positive 1. Those are all vertical asymptotes. Those are lines I can fill in on the sketch here in just a minute to kind of guide the graph. As far as any additional guidance is concerned, horizontal asymptote, remember this is where we compare degrees. Degrees in the numerator, degrees in denominator. If you're looking at your original function, that 1 over x cubed minus x, and you look at the degree in the numerator, well, degree in the numerator is what? 0, there's no x. And in the denominator, highest power of x is 3, so degree is 3. Meaning, degree in the numerator is less than degree in the denominator. Whenever that happens, horizontal asymptote is y equals what? Remember? 0. All right, finally got all our information. Finally ready to make our little drawing here. So let's take some of the latter information here. Let's take some of these asymptotes, start filling in some lines here on our graph. We know that we've got vertical asymptotes at negative 1 at 0 and at 1. Once again, go back to those charts, first and second derivative charts, see where stuff does not exist. That makes sense. We've got a horizontal asymptote where y equals 0. So that's just going to travel here along the x-axis. far as asymptotes are concerned, that's all we got to play with. As far as intercepts are concerned, we didn't find any. So now what I'm going to do is I'm going to work my way back to specific points from the first derivative chart and the second derivative chart. Any specific points that we had. So first derivative chart, second derivative chart. Here's the second derivative chart, where we got all excited about the potential that we had inflection points, but then we found that nothing really worked out. So no points there, right? There's no values to play with here in this F column, so there's no points there. If we go back to the first derivative chart, we have specific values. We have one right here, when x is negative 0.577. We've got one right here, when x is 0.577. After all this work, we have two actual points to plot here. 2 points we can play with. So let's plot those points. All right, so those points again, we had negative 0.57 and 2.598. If I approximate those, well, let's see here, negative 0.57, go up to about 2.6, roughly right there. And then 0.577 and negative 2 point roughly 6. That's going to be, in this proximity right here. Yay, 2 points. Okay, now I'm going to go back to the first derivative chart so I can start filling in direction. As I fill in direction, I could get an idea of what the curvature looks like, but remember, that's second derivative stuff, so I'm not going to be overly specific about the curvature yet. As far as direction is concerned, from negative infinity to negative 1, so as you think about the sketch you got sitting there right now, this is up to that first vertical asymptote. We know that the graph is decreasing. And then from negative 1 to negative 0.577, up to our first point. So from the asymptote up to that first point, we know the graph is decreasing. How that transfers over? Well, let's see. If it's decreasing until I get to this asymptote here, the whole idea of having this horizontal asymptote is it guides the end behavior. So I'm going to need to start this somewhere right about there and bring it down if it's decreasing. Now I'm kind of anticipating what the curve looks like already. We'll see how that matches up with the second derivative chart in a minute. If that horizontal asymptote is there guiding the end behavior, roughly that direction would have to look something like that. And again, it was decreasing once we got to the asymptote and went up to our first point here. So that means decreasing would have to look something like this. Now, once we get past that point, well, from that point to the next asymptote at x equals 0, graph's going up. And from that asymptote where x is 0 to our next point at 0.577, graph is also going up. So it's going up from this point to the next asymptote. And then from that asymptote, it's going up to the next point. Looks something like that. Now from that point forward, let's fill in these last couple of intervals. From that point forward, we got all kinds of decreasing going on, right? It's decreasing up to the next asymptote. It's decreasing past that asymptote. So we're getting close here. From this point forward, it decreases. From that asymptote forward, it decreases, but we got to be mindful of the horizontal asymptote again. It's got to guide the end behavior. So it's decreasing here, guiding the end behavior, kind of anticipating what the curve would look like. It may look something like that, but we got the direction down, right? So now just fill in the curvature. Where's the concave up? Where's the concave down? That's brought to us by the second derivative chart. So it is concave down from negative infinity to negative 1. So everything up to that vertical asymptote. It's concave up from that first vertical asymptote to the next one, right? Because the next one where x was 0. And basically there's this rotation as you go from asymptote to asymptote. From 0 to 1, it's concave down. From 1 to infinity, it's concave up. So let's see if we can sync that up. If we can, we'll be done. And that's the most important part, right? So concave down for everything up to this vertical asymptote. It's got to decrease as well. Curvature has to be downward. If we exaggerate a little bit, it could look something like that, right? It's concave up from this asymptote to this asymptote. Has to go down here, but be concave up. Has to go up here, but be concave up. Could look something like that. From x equals 0 to x equals 1, next set of vertical asymptotes. Well, let's see, it's got to be concave down, so it's got to increase here, be concave down, decrease here, be concave down. And then last interval, from last asymptote on out, has to be concave up, also has to decrease. Looks something like that. There's our curve of the original function, piecing together everything that we know at this point.